Welcome to another deep dive, everyone. Today, we're going to be focusing on some new and pretty interesting findings about Uranus's magnetosphere.
Yeah.
And all this is based on a recent analysis of data from Voyager 2, the only spacecraft to ever, actually fly by the planet.
Yeah, that's right. We're talking about Voyager 2's flyby from way back in 1986. It's pretty incredible that we're still getting these new insights from this mission almost 40 years later.
It really is. So for anyone who needs a refresher, Voyager 2's flyby gave us our first real look at Uranus's magnetosphere, which is basically this region around the planet that's dominated by its magnetic field. And what Voyager 2 found was, well, let's just say it was pretty puzzling.
Puzzling is putting it lightly. Voyager 2 detected these super intense electron radiation belts, like way stronger than scientists expected. But here's the thing. The rest of Uranus's magnetosphere seemed strangely empty, like it was lacking the plasma. That's the superheated, electrically charged gas needed to generate such powerful radiation belts. It was almost like finding a roaring fire with no fuel to keep it going,
So it's like, where were all these energetic electrons coming from?
Exactly. At first, scientists thought that maybe Uranus's 5 major moons, the ones that are, nestled inside its magnetosphere, were geologically inactive. You see, active moons, like some of the ones we see around Jupiter and Saturn, they release these things called ions, which are just atoms that have either gained or lost electrons. And these ions can contribute to a planet's magnetosphere and, energize those radiation belts.
So the thinking was, no active moons equals no ions, which means there's no fuel for the radiation belt fire. Makes sense. But that's where this new research comes in, right?
Right. This new analysis suggests that what Voyager 2 observed might not have been Uranus's typical magnetosphere. It seems like the spacecraft flew by during a pretty rare space weather event where the solar wind was actually compressing Uranus's magnetosphere.
Okay, so how rare are we talking here?
Well, based on modeling, this kind of compression probably only happens about 4% of the time. So Voyager 2 basically caught Uranus in a very unique state. And a very temporary state.
Wow, talk about being in the right place at the wrong time.
Or maybe the right time for a scientific puzzle. Think of it this way. Imagine you're trying to understand a city's typical traffic patterns, but you only get to observe it during a massive rush hour jam caused by some, really rare event.
Okay, yeah, I see where you're going with this. Voyager 2 basically flew through during rush hour, so to speak, and saw like a really distorted picture of what was actually going on.
Exactly. This compression from the solar wind probably squeezed plasma out of the system, which would explain why Voyager 2 observed such low plasma levels. And at the same time, this compression would have temporarily intensified the dynamics of the magnetosphere. So it basically pumped up those radiation belts. It was basically just a snapshot of a magnetosphere in a very unusual compressed state.
So it wasn't necessarily representative of Uranus's magnetosphere on an average day. And that kind of changes things when it comes to those potentially inactive moons, right?
It definitely does.
Yep.
This new research is suggesting that those moons might not be so inactive after all. They could be releasing ions and contributing to the magnetosphere, but Voyager 2 just happened to miss the full picture, all because of that unusual space weather events.
Hold on, are we saying that those moons might actually be geologically active, like spewing out plumes of stuff, and maybe even harboring, hidden oceans beneath their icy surfaces?
Well, we don't have, definitive proof yet, but it's definitely a possibility that's worth exploring. After all, some of the most exciting discoveries in our solar system in recent decades have involved these icy moons around gas giants, places like Europa around Jupiter and Enceladus around Saturn. These moons are incredibly active, with evidence of cryovolcanoes, subsurface oceans, and even...
Hang on, cryovolcanoes. You're going to have to explain that one.
Sure. Cryovolcanoes are kind of like volcanoes here on Earth, except instead of molten rock, they erupt with water, ammonia, or other volatile materials. Just imagine geysers shooting plumes of ice particles and vapor hundreds of kilometers into space.
That is wild. Okay, so if moons like Europa and Enceladus can be that active, maybe. Just maybe. Uranus's moons are hiding similar secrets, and Voyager 2 just missed the show because of this solar wind compression.
It's a tantalizing possibility, and one that this new research makes much more plausible.
Okay, I am officially intrigued, but we're just getting started, right? What other implications does this have, especially when it comes to those intriguing Uranian moons? Let's dive deeper after a quick break.
Absolutely. There's a lot more to unpack here. Stay tuned.
Okay, so right before the break, we were talking about how this new analysis of Voyager 2 data is really changing our understanding of Uranus's moons. Like, we went from assuming they were inactive to, well, maybe they're not so quiet after all.
Yeah, exactly. And this shift in thinking has really reignited interest in these moons, especially considering everything we've learned about other icy moons in our solar system.
Right, like those crazy cryovolcanoes we were talking about. Those are pretty hard to ignore.
Yeah, they're pretty spectacular. They're a spectacular display of, geological activity. And what makes them especially interesting is that they often hint at something even more intriguing, subsurface oceans.
Okay, wait. You're saying there could be vast oceans hidden beneath the icy shells of these moons?
That's the idea. Take Europa, for example, one of Jupiter's moons. Scientists think that it has a global saltwater ocean beneath its icy surface, potentially containing more water than all the oceans on Earth combined.
Whoa, are you serious? That's mind-blowing. But how do they even know that? It's not like we can just, peek under the ice.
Well, it's a combination of different clues. We've observed these plumes of water vapor erupting from Europa's surface, and its magnetic field hints at a layer of electrically conductive fluid beneath the ice, which is most likely a salty ocean. And then there are these chaotic terrains on the surface, which suggest geological activity driven by tidal forces and the movement of that subsurface ocean.
So like Jupiter's gravity is kind of tugging on Europa?
Yeah.
And that's causing friction and heat.
Yeah.
Which keeps the ocean liquid.
Yeah.
And drives all this, activity.
Exactly. It's a fascinating example of how gravitational interactions can create these pockets of energy and activity in these seemingly inhospitable places, And what's really exciting about these subsurface oceans is their potential for habitability.
Habitability? You mean like alien life?
Potentially, yeah. We know that life, as we understand it, requires water, a source of energy, and certain chemical building blocks. And some scientists think that these subsurface oceans could provide all three.
Okay, I need to hear more about this. How could a hidden ocean on an icy moon possibly support life?
Well, think about it. In these dark, isolated oceans, life wouldn't rely on sunlight like it does on Earth. Instead, it might draw energy from hydrothermal vents on the ocean floor.
Hydrothermal vents, those are like underwater hot springs, right? I kind of remember learning about them in school.
That's right. They're found in Earth's oceans, often along mid-ocean ridges where tectonic plates are spreading apart. These vents spew out these hot, mineral-rich fluids from deep within the Earth, creating these unique chemical environments that support thriving ecosystems, even without any sunlight.
So you're saying there could be similar vents in these subsurface oceans on other worlds, providing energy and nutrients for microbial life.
Exactly. And what's really fascinating is that some scientists think that hydrothermal vents might have even played a role in the origin of life here on Earth. So finding evidence of similar processes on other worlds would be, a major discovery.
Wow, okay. I'm starting to see why everyone's so excited about these icy moons. But let's get back to Uranus. Are we saying that its moons could have similar subsurface oceans and hydrothermal vents?
Yeah.
And maybe even microbial life?
We can't say for sure without further exploration, but it's definitely a possibility that's worth investigating. And that's why this new research on Uranus's magnetosphere is so important.
Because it suggests that the moons might be more active than we thought, which means there's a better chance of finding those intriguing features.
Exactly. And this kind of ties into a larger conversation happening in the planetary science community.
Right.
About the need for a dedicated mission to Uranus.
Right. I remember hearing about that. A mission to Uranus was actually ranked as a top priority by the national academies in their decadal survey, right?
It was. The 2023 Planetary Science and Astrobiology Decadal Survey identified a Uranus orbiter and probe as one of the most compelling missions for the coming decade. And this new research just gives that recommendation even more weight.
Okay, but I'm curious, what would a mission like that actually look like? And what kind of insights could it provide?
Well, a Uranus mission would probably involve a spacecraft that orbits the planet for a few years, studying its atmosphere, magnetosphere, and rings in detail. But maybe most importantly, it would carry instruments to observe those, intriguing moons, searching for evidence of geological activity, subsurface oceans, and, dare I say, signs of potential habitability.
So we'd be talking about a mission that could potentially rewrite our understanding of ice giants, and maybe even reveal whether we're alone in the universe.
It's an ambitious goal, but that's what makes it so exciting. A mission to Uranus would be a journey into the unknown, with the potential for discoveries that could fundamentally change our perspective on our place in the cosmos.
And it all started with Voyager 2. a mission that was launched almost 50 years ago. It's incredible to think that data collected way back then is still driving new discoveries and shaping our exploration plans for the future.
It really speaks to the power of scientific exploration and the importance of thinking long-term. Who knows what other secrets are hidden within Voyager 2's data, just waiting to be unlocked, and what other wonders await us as we, keep pushing the boundaries of our knowledge and venture further into the unknown.
It really makes you wonder what other mysteries are out there just waiting to be discovered. But for now, let's shift our focus back to the practical side of things. If those Uranian moons really are active, what kind of geological processes might we expect to find? Let's delve into that after a quick break.
Sure. Stick with us.
Okay, so we've been on this incredible journey exploring the mysteries of Uranus's magnetosphere and the exciting possibility of active moons. But before we finish up, let's bring it back down to Earth for a minute.
Yeah, sounds good.
So let's say those Uranian moons really are as geologically active as we're speculating. What kind of specific features or processes might we actually find? What would make these moons, unique compared to, say, Europa or Enceladus?
Well, that's a great question, and it's where things get really interesting. See, Uranus's moons are in a pretty unique position in our solar system. They orbit an ice giant that's tilted on its side, which means they experience some really extreme seasonal variation.
Wait, tilted on its side. I'm picturing Uranus spinning like a barrel rolling through space.
Yeah, that's a pretty accurate picture. And because of this tilt, Uranus's poles point directly at the sun for these long, extended periods, creating these incredibly long seasons. Imagine a single season lasting, decades.
Wow, that's crazy. So how would that affect the moons?
Well, those extreme seasons could lead to some, pretty dramatic changes on the moon's surfaces. Imagine ice melting and then refreezing over and over, creating all these cracks and fissures. Or even triggering geological activity like, cryovolcanism. We might even see evidence of this in the form of surface features that are totally different from anything we've seen on other icy moons.
So we're talking potentially unique geological formations, maybe even cryovolcanic features that have been shaped by these crazy seasons.
Exactly, and that's just one example. Another fascinating thing is the composition of Uranus's moons. They're thought to be made up of a mixture of rock and ice with a lot of ammonia and methane.
Ammonia and methane, like the stuff that makes Uranus smell so unique.
Well, we can't really smell Uranus from Earth. But yes, those compounds are definitely present in its atmosphere. And they could play a role in the geology of its moons, too. For example, methane clathrates, which are basically these ice-like structures that trap methane molecules, could exist beneath the surface of these moons. And if these clathrates melt or decompose, they could release methane, potentially fueling cryovolcanic eruptions, or even contributing to the formation of those subsurface oceans we were talking about.
So we could be talking about moons with a totally different type of cryovolcanism compared to what we see on Europa or Enceladus.
Exactly. The chemistry of these moons could lead to some, really unique and unexpected geological processes, and that's what makes them so interesting to study.
Okay, this is seriously blowing my mind. So to recap, we've got these Uranian moons that might be way more active than we thought, all thanks to this new analysis of Voyager 2 data. We're talking potential cryovolcanoes, subsurface oceans, and maybe even the ingredients for life. And on top of all that, they experience these crazy seasonal extremes and have this unique chemical makeup that could lead to all sorts of, unexpected geological phenomena.
You got it. Uranus's moons are like these hidden gems in our solar system, just waiting to be explored. They could really challenge our understanding of planetary processes and maybe even reveal new possibilities for life beyond Earth.
It's amazing to think that we're just scratching the surface of what's out there. So as we wrap up our deep dive into Uranus's magnetosphere and its amazing moons, what's the one key takeaway you want our listeners to remember?
I think the most important thing to remember is that our solar system is full of surprises. We're constantly learning new things and refining our understanding of these incredible worlds. And sometimes the most incredible discoveries come from looking at old data in new ways, asking new questions, and, daring to imagine what might be possible.
That's a great point. It just goes to show that the spirit of exploration and scientific curiosity is what drives us to, push the boundaries of knowledge and uncover the secrets of our universe. So to all our listeners out there, keep looking up, keep asking questions, and never stop exploring. Who knows what awesome discoveries await us in the future?
Yeah, there's a whole universe out there waiting to be discovered.
Thanks for joining us on this deep dive, everyone. And until next time, keep exploring.